Okay, this is a quick review for the bonding test that you're going to have on Monday. And so when you go through here, if you take notes on your review, then you'll be able to use those on your test on Monday. But your review has to be complete. So the first thing we're going to go over is electron configuration, because you will have some electron configuration on your test.
That's where I left my glasses in here.
Okay. And for electron configuration, you need to remember that there are 4 different types of orbitals. We have S, P, D, and F. And an S orbital is sphere-shaped. A P orbital is dumbbell-shaped. And then these two, this one's a double dumbbell. And this one's just really complicated, so we're not going to worry about that one. All right, we know that in an S orbital, it can hold a max of 2 electrons, a P can hold 6, a D can hold 10, and an F can hold 14. So every time that we're filling up rings around the nucleus, we're filling up these types of orbitals. In the very first ring around the nucleus, we can have an S orbital, which means our total is 2 electrons. In the second ring, we have an S and a P, which means we have a total of 8, because that would be 2 plus the 6. In the third ring, we have an S, a P, and a D, which means 2, 6, and 10, so we have 18. And then in the fourth, we have S, P, D, and F, which gives us 32, and then so on. So you need to make sure that you understand how many electrons can be in a ring around the nucleus. And then we also had 3 of the rules when we were doing electron configuration that you need to go back and look in your notes and make sure that you know what they mean. You need to know what Hund's rule is. And I called that the empty bus seat rule. And then you have the principle that's the order of lowest energy. That's called the Aufbau principle. That tells you what order the electrons fill their shells, order of filling. And then you also have the Pauli exclusion principle. And that's the one where we talked about the arrows have to be one up and one down. You can't have 2 arrows for the electron configuration that are the same, going up or down. So if we're doing an electron configuration for, let's say, sulfur. Sulfur is element number 16, element number 16. So we would go 1s2, 2s2, 2p6, 3s2, 3p4. That gives us 2, 4, 10, 12, and then that gives us 16 electrons. So this would be the longhand electron configuration. If we wanted to do the orbital notation for this, we would take these 2 electrons, and instead of putting the superscript, we would put arrows up and down. And then arrows up and down. And then for the P, you would have 3 sets of arrows, and you would go up, 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 down, 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 and so on and so forth until you fill them all up. Okay, so that's pretty much everything on electron configuration. Make sure that you can look at an electron configuration like this and tell me what element it is. So that means you need to be able to count, and then you would know that that's element 16, 16 electrons. Okay, the next thing is the Lewis dot structure. When we do a Lewis dot structure, just very quickly, this is showing us valence electrons only. And valence electrons, when we're drawing the Lewis dot structure, we're talking about if they fill the s and the p orbitals, then that means that this is satisfying the octet rule. Oops, that should be satisfies the octet rule. Okay, so if we do the Lewis dot structure for, let's say, hydrogen, we look at the Roman numeral, and that would have a Roman numeral of 1, so we would just put 1 dot. If we look at calcium, we would have 2 dots. If we look at sulfur, we should have 6 dots. If we look at nitrogen, we would have 5. Now, when you're putting your dots, guys, you're about to go to your desk and sit by yourself quietly and work, because I seriously doubt you're getting much done. Make sure that you do single electrons around it first, and then you pair them up. So this one would have 5. If I have something that has 4 electrons like carbon, this would be correct. You would not see it written like that or like that. It needs to be 4 of them by themselves. And the valence electrons are used to draw the Lewis structures and the molecular structures for the Lewis diagrams. So let's look at an example of at the different types of bonds real quick. Okay, we have 2 different types of bonds. We have ionic and covalent. And then we'll add metallic kind of in the bottom at the end. So for ionic bonds, you need to know the difference between all of the different types of bonds. And for an ionic bond, we are talking about a transfer of electrons between positive and negative ions. And you need to know a positive and a negative ion is called a cation or an anion. And so this would be called a cation. This would be an anion. Okay, those are the 2 things that you have in an ionic compound. These happen between metals and nonmetals. All right, so a metal would be a positive cation because it loses electrons, and a nonmetal would be a negative anion because it gains metals. The reason this happens is because of electronegativity. Okay, electronegativity, if it's very different, then you're going to have this kind of bond. You're going to have an ionic bond. And the reason you have an ionic bond is because metals have a low, you need to remember that, write that down. Metals have a low electronegativity, and nonmetals have a high electronegativity. So that means that nonmetals pull the electrons off the metals, and that's why you get an ionic bond with a charge. Now for covalent bonds, there are no charges. So you need to, if you ever see a bond with a charge on it, it can't be covalent, it has to be ionic, because there are no charges in covalent bonds. Covalent bonds, we are sharing electrons. And they are between nonmetals. So we are talking about nonmetals sharing electrons. If they share equally, like chlorine and chlorine, then that would be nonpolar. If they share unequally, like hydrogen and chlorine, then that would be polar. Okay, and then the third type of bond would be between metallic, between different types of metals. And when you have a metallic bond, remember you just have a sea of electrons. And the sea of electrons is what causes metals to conduct electricity. I know you have some test questions specifically about metallic bonding. So, conducts electricity, it's malleable and ductile. Okay, if you remember, ductile means that it can be pulled into thin wires, malleable, hammered into thin sheets, conducts heat and electricity, is pretty self-explanatory. So those are the three different types of bonds that we talked about with this unit. All right, and then we talked about something called the VSEPR theory. And with the VSEPR theory, this is talking about how electron pairs repel each other. And they determine the shape of the molecule. Okay, now if they determine the shape of the molecule, the reason that happens is because the electrons repel each other, so they are trying to minimize the electron repulsion. So you need to be able to look at the different shapes and know, look at a molecule and know what shape that would be. So for example, if I have, first of all, let's look at this and do a couple things on it. This has 4 pairs of electrons. That are shared, and because it is a double line here and a double line here, those are 2 double bonds. Okay, so we have 2 double bonds with our C and O's. And this would be a linear shape. Now, if I had something like this, I have 4 single bonds. And since I have 4 single bonds and no lone pairs of electrons, this would be tetrahedral. So you need to know the names of those shapes. You may want to write them down on your notes so that you have them. Okay, so let's talk about just a few more things. Lewis dot. We've got the Lewis dot for covalent versus ionic, because you need to know the difference between them. And we drew those on page 13. The difference between ionic and covalent. When you draw a Lewis dot structure for covalent, something like this, versus ionic, something like this. When we drew this, we drew an arrow over there showing the electron being moved. So the dot structure for this would be potassium with a +1, and then fluorine actually now has 8 electrons, and it would be a -1. So when you see charges in a dot structure, that tells you it has to be ionic. Covalent, no charges. Charges. Okay, so charges versus no charges. And then what if you had 2 more things? If you had 2 different elements, you need to be able to tell me what type of bond you would form. So if I had calcium and sulfur, you look on the periodic table, this is a metal, this is a nonmetal, so metal plus a nonmetal is ionic. If I had sulfur And oxygen, S and O, that would S and O, that would be a nonmetal plus a nonmetal, so that would be covalent. So make sure you can tell the difference between what kind of bond it would be just by the elements and where they're found on the periodic table. And then the very last thing is, when we did the flame test lab and you heated up the elements in the Bunsen burner, what you were doing, you were causing the electrons to become excited and move up to a higher energy level, and when they came back down, they gave off the color. And so what you're looking for is, if I have an electron configuration of an atom, let's say 1s2, 2s2, 2p6, and I put that atom in the flame, some of these electrons in the outer ring can jump up to the next one. So a possible configuration for this now could be that. If you ever see an electron configuration where it is not there, there's been an electron that's jumped up to another level and then it didn't fill this level up, that means it's in the excited state. And when it comes back down, it's going to give off light. Alright, so if you have pages 21 through, is it 21 through 26? 21 through 26 done, and notes from the video. You can use them on your test on Monday. The test has to be completed during the class period on Monday, so study and be ready.